As many can attest, when you join the censored Earth community, you are given a new set of eyes. Now, I've studied Earth science before, but now that I've been given a new set of eyes, I'm going to go back and take another look and tell you what I see. This is modern Earth science destroyed.
Welcome to Chapter 2, Earth in Space. To get us started, let's read this description and then talk about what is wrong with this opening picture.
During one of the Apollo missions to the moon that began in 1969, an astronaut snapped this picture of the Earth above the surface of the moon. For the first time in history, people could view the beautiful blue Earth suspended in the blackness of space. Since that time, space exploration has added much to the knowledge of the Earth. This chapter describes the Earth, its movements through space, and the use of spacecraft to explore the Earth.
Do you believe all that about astronauts going up and taking this photo from space?
No?
Okay, so what is wrong with this picture?
I like this observation my friend Rodrigo pointed out to me. The sky is well known to change colors in the morning and in the evening. Yet here, we don't see any changes in color as it turns from night to day.
That is such a cool observation. That would actually make space photos even more beautiful. So here's an observation I don't think I've ever heard anyone mention before. Where do you think the sun is in this picture?
Above the viewer?
Yeah.
You know, for having the sun directly above you, if this picture was real, I should think the moon would be a lot brighter than that. And the moon would seem a lot more two-dimensional.
Two-dimensional. Tell me more.
It's interesting how, when we look at the moon here, it is darker up close and it gradually gets lighter out in the distance. In college, I was taught about how artists often paint things up close in the foreground darker, and things in the background lighter, in order to create a sense of depth.
I remember learning that. We see that effect all the time in nature because of the atmosphere.
Yet here we appear to be seeing the same effect taking place on the surface of the moon, where there is supposed to be next to no atmosphere. We can see the same thing on the ground in this picture here. And in this picture. And you can really see it strong in this picture here. It is all over the place when photographers want to create that sense of depth.
That's a good point. But that wasn't what I was going to say. If the sun is directly above us, and if this is Australia, then here is north, east, south, and west. Now, according to NASA, the moon actually moves from west to east around the Earth. But because the Earth is spinning, it only looks like the moon moves from east to west. So here's my question. If west is up and the moon is moving west at 2,228 miles per hour, how are the astronauts who are floating in the air and taking the picture not total bug splat?
Whoa, that is a really good question. Yeah, as we look at it, we've got to remember that the Earth, the moon, and the spacecraft are all supposedly moving at crazy, ridiculous speeds. Yet somehow we don't see any motion blur anywhere.
That would have had to have been one amazing camera. I wish my phone camera had that good of technology. All right, let's continue reading. Earth, a unique planet.
Photos of the Earth from space reveal a blue sphere covered with white clouds. Surrounded by the blackness of space, the Earth appears beautiful, yet fragile. In fact, the Earth is unique in the solar system. It is the only known planet with liquid water on its surface, and an atmosphere that contains a large amount of oxygen. Most important, the Earth is the only planet known to support life.
You might even say the Earth doesn't even resemble any of the planets we see in the sky. Statistics.
Viewed from space, the Earth appears to be a perfect sphere. On a perfect sphere, The circumference or distance around is the same no matter where it is measured. However, careful measurements reveal that the Earth's circumference varies slightly, depending on where it is measured.
I wonder what measurements they are talking about there. Is there a place where we can see those measurements for ourselves?
You got me on that one. The circumference measured around the poles is 40,007 kilometers. The circumference measured around the equator is 40,074 kilometers. The equator is an imaginary line that divides the Earth into northern and southern hemispheres. Because of these differences in the Earth's circumference, the Earth is more accurately described as an oblate spheroid, a slightly flattened sphere. The spinning of the Earth on its axis causes the polar regions to flatten and the equatorial zone to bulge. The Earth's axis is an imaginary straight line running through the Earth from the North Pole to the South Pole.
Earth, we know it spins once a day. Yes, thank you. 3 people know how long a day lasts here.
Good for row number 2. They're off to a great start.
So you spin. You know, when you spin pizza dough, it kind of flattens out.
Yeah.
It gets wider in the middle, and so Earth, throughout its life, even when it formed, it was spinning, and it got a little wider at the equator than it does at the poles. So it's not actually a sphere; it's oblate, and officially it's an oblate spheroid. That's what we call it. But not only that, it's slightly wider below the equator than above the equator.
A little chubbier.
A little chubbier.
Yeah.
Chubby's a good way. It's like pear-shaped.
Yeah.
Goodness, our guy on the inside strikes again!
Either that or the entire world has suddenly become obese since the 1960s.
Seen from space, the Earth's surface also appears to be smooth. Given the size of the planet, its surface is relatively smooth. The difference between the height of the tallest mountains and the depth of the deepest ocean trenches is only about 20 kilometers. This distance is relatively small compared to the Earth's average diameter of 12,735 kilometers.
The hydrosphere and the atmosphere.
The Earth is 71% covered by water, and about 97% of that water is in the salty oceans. The remaining 3% of the Earth's water is in fresh water that is found in lakes, rivers, and streams, and that is frozen in glaciers and the polar ice sheets. All the Earth's water makes up the hydrosphere. The Earth is surrounded by a blanket of gases called the atmosphere. The atmosphere provides the air you breathe and shields the Earth from the sun's harmful radiation. The atmosphere is made up of 78% nitrogen and 21% oxygen. The remaining 1% includes other gases, such as argon, carbon dioxide, and helium.
You know, I'm pretty sure those numbers are constantly changing. I wonder how or when anyone has ever measured the entire atmosphere. The Earth's interior.
Direct observations of the Earth's interior is impossible, so scientists must rely on indirect methods to study it. For example, scientists have made important discoveries about the Earth's interior through studies of seismic waves. Whoa! They are referring to the discoveries of unnamed scientists again. Let's underline that for our people on our debate board who want to defend the book and go through and fill in all the blanks. What scientists are they talking about here? Seismic waves are vibrations that travel through the Earth. Earthquakes and explosions on or near the Earth's surface produce seismic waves. By studying seismic waves as they travel through the Earth, Scientists have determined that the Earth is made up of 3 major zones.
I don't really think they speak for all scientists here.
If they do, I would love to see the survey that was put out that came back with a unanimous vote to sustain this claim.
I don't doubt that some scientists have come to this determination, though.
Yeah, neither do I.
Zones of the Earth.
The thin, solid outermost zone of the Earth is called the crust. The crust makes up only 1% of the Earth's mass. Mass is the amount of matter in an object. Beneath the oceans, the crust is called oceanic crust. Oceanic crust is only 5 kilometers to 10 kilometers thick.
There they go again. They're making it sound like the entire ocean floor has been discovered already.
The part of the crust that makes up the continents is called continental crust. The continental crust varies in thickness from 15 kilometers to 80 kilometers. Continental crust is the thickest beneath high mountain ranges. Below the crust lies the mantle, a zone of rock nearly 2,900 kilometers thick. The mantle makes up almost 2/3 of the Earth's mass and is divided into 2 different regions.
And there they go, acting as if they knew exactly how much mass the Earth had. A person can only say what 2/3 of something is if they know what 100% of something is.
And now I'm hungry for pie. The uppermost part of the mantle is cool and brittle. This part of the mantle and the crust above it make up the lithosphere, a rigid layer 15 kilometers to 300 kilometers thick.
And because I'm feeling generous, I will help support the book's claim here. This claim is verifiable in one location anyway. According to scientificamerican.com, the deepest hole ever dug is the Kola Super Deep Borehole, which is 12,000 kilometers deep. Shoot. Okay, wait a second. Never mind. There seems to be some disagreement on that one. The BBC claims it was only 12 kilometers deep. That is a lot different than 12,000 kilometers deep. I guess it wasn't as verifiable as I thought.
Thanks a lot, Google. Just below the lithosphere is a region of the mantle called the asthenosphere. The asthenosphere is approximately 200 kilometers thick. Because of enormous heat and pressure, the solid rock of the asthenosphere has the ability to flow. The ability of a solid to flow is called plasticity. Below the mantle is the core. It forms the center of the Earth and is made mostly of iron. From seismic studies, scientists think the outer core is a dense liquid layer about 2,250 kilometers thick.
Yeah, this is a good example of where I'd like to see that survey you were asking about. The one that went out to all the scientists in the world and came back with a unanimous vote.
The inner core is a dense, solid sphere with a radius of 1,228 kilometers. The inner and outer core together make up nearly 1/3 of the Earth's mass.
Oh, now you've got me craving pie. I would sure like to know how they claim to have determined what the entire Earth's mass was. Seismic wave studies.
2 types of seismic waves, primary waves, or P waves, and secondary waves, or S waves, are useful to scientists exploring the Earth's interior. P waves and S waves behave differently. P waves travel through liquids, solids, and gases. S waves travel only through solids. P waves also travel faster than S waves. The speed and direction of both types of waves are affected by the composition of the material through which they travel. Both P waves and S waves travel faster through more rigid materials. The speed and direction of seismic waves reveal much about the Earth's interior.
It's unfortunate they don't show us what P waves and S waves look like. It would be nice to observe them for myself here.
2 types of seismic waves are made, and each is quite different. P waves. These waves travel the fastest and are called primary waves or pressure waves, as they arrive at a distant location first. These waves compress and stretch the rocks as they spread out. P waves pass easily through both solids like rock and liquids like magma. S waves. These slower waves arrive after the P waves, and so are called secondary waves or shear waves. S waves cause an up and down motion. They travel through solid but not liquid.
Well, that is certainly something better than the book shows. Thank you, YouTube. A lot of people say textbooks are better. In this case, you have proved yourself to be better than the book. However, I would still like to see an actual real-life observation of this, and not just a mere illustration of it. Let's read about the Moho.
In 1909, Andrija Mohorovicic, a Croatian scientist, discovered that the speed of seismic waves increases abruptly 32 kilometers to 70 kilometers beneath the Earth's surface. Hooray! They actually named a scientist! We have a who, we sort of have a where, we have a when, now we just need to know how.
Well done! They finally named a scientist.
As figure 2-2 shows, this change in the speed of the waves marks the boundary between the crust and the mantle. This boundary is called the Mohorovicic discontinuity, or the Moho. The increase in speed at the Moho indicates that the Earth's mantle is denser than its crust.
Huh. Just looking at this diagram, the inner core is 6,000 kilometers deep. Earlier, we talked about how the deepest hole ever dug was 12 kilometers deep. How did they reach the inside of the core to measure the speed of the waves there?
You got me on that one. I have no idea. Maybe the Scientific American got it right, and they got through 12,000 kilometers after all. Below the Moho, at a depth of about 100 kilometers, a decrease in seismic wave speed marks the boundary between the lithosphere and the less rigid asthenosphere. Seismic waves then increase in speed until, at a depth of about 2,900 kilometers, P waves slow down again, while S waves disappear entirely. These changes in the seismic waves mark the boundary between the mantle and the outer core. Because S waves cannot travel through liquids and P waves slow down in less rigid materials, scientists think the outer core may be a dense liquid.
I'm just wondering, if S waves cannot travel through liquids, how does the globe Earth claim these waves get past the water table?
Water that collects underground is held in an upper unsaturated zone and a lower saturated zone. The unsaturated zone is located directly beneath the land surface, and the pore spaces hold both air and water. In the saturated zone, all the open spaces are filled with water. The water table is the very top of the saturated zone and the bottom of the unsaturated zone.
I think we've got quite a few unanswered questions here. Now, we're not saying that they are wrong just because we don't understand how their model works. That would be committing the incredulity fallacy.
What we are saying is if they want to convince us that their model is right, they're going to need to provide us with better explanations and evidence in order to do so. There is nothing wrong with saying that.
At a depth of 5,150 kilometers, P waves speed up again, marking the boundary between the outer core and the inner core. This increase in speed suggests that the inner core is a dense, rigid solid. And again, I would like to know how they measure the speed of the waves in the inner core.
Shadow zones.
Recordings of seismic waves around the world reveal shadow zones on the Earth's surface. Shadow zones occur because the materials that make up the Earth's interior are not uniform in rigidity. When seismic waves travel through materials of differing rigidities, their speed changes, causing the waves to bend and change direction. As Figure 2-3 shows, a large S-wave shadow zone covers the side of the Earth that is opposite an earthquake. S-waves do not reach the S-wave shadow zone because they are blocked by the liquid outer core. Although P-waves can travel through all the layers, the speed and direction of the waves change as the waves pass through each layer. The waves bend in such a way that a P-wave shadow zone forms.
Earth as a magnet.
If you have ever used a magnetic compass to find direction, you know that the Earth acts like a giant magnet. Like a bar magnet, the Earth has two magnetic poles. However, it's interesting to note that Discover magazine claims that the Earth has 4 north poles.
With that being the case, I wonder how many south poles people claim the Earth has.
As Figure 2-4 shows, the lines of force of the Earth's magnetic field extend between the northern geomagnetic pole and the southern geomagnetic pole. The Earth's magnetic field also affects the area that extends beyond the atmosphere. This region of space, which is affected by the Earth's magnetic field, is called the magnetosphere. The source of the Earth's magnetic field may be the liquid iron in the Earth's outer core.
So this magnet is so strong I can pick up these paper clips from like a whole foot away, right? So what I've done here is I've stuck the magnet to a piece of metal in the ground so it's parallel to the thermite. So when it goes off, we'll see if the metal stream gets attracted to the magnet or not, and if it doesn't, it'll just fall straight to the ground. We'll see if it bends. All right, here we go. 3, 2, 1. So that thermite turned the wooden bowl into a raging firestorm, but I'm beginning to think that there's no reaction between molten metal and magnets. In fact, I think that molten metal and magnets don't mix very well at all. That was pretty cool. I might have broken my magnet though. It was completely engulfed in the flames right there, but it's not very hot. Okay, it's kind of hot, but not like destroyed hot. Once magnetic materials reach a certain temperature, they lose their magnetism. That's 600 for this magnet and 1400 degrees Fahrenheit for iron. This is called the Curie point, and below it the magnetic fields are nice and aligned, but above it, they're totally random. This is why we don't see any attraction between the molten iron and the thermite. The iron hasn't cooled enough to align into a magnetic field yet. Yeah, so this is the wood bowl that the thermite fell into. There's not much left, but it's got a pretty cool pattern in there. Now I just want to see how much iron is in here, so see if it grabs it. Oh yeah, there's a big chunk of it. And it's pinching me, ow! Oh, that really hurt. The magnet actually pulled that metal so hard, it cut me when it hit my finger. So these things are no joke.
Thank you, YouTube. Because iron is a good conductor, scientists hypothesize that motions within the core produce electrical currents that in turn create the Earth's magnetic field.
I've got to say, this is something nice to see. The authors of the book actually coming out and saying they don't know something. We don't see that very often.
Research, however, indicates that there may be another source for the magnetic field. Scientists, who have not been mentioned, have found that both the sun and the moon have magnetic fields. Yet the sun contains very little iron, and the moon does not have a liquid core. Discovering the sources of the magnetic fields of the sun and moon may help scientists identify the source of the Earth's magnetic field.
It is unfortunate they don't mention how they claim to know what the inside of the moon is made of. It's like the authors can't make up their minds as to whether they know everything or not. All right, let's talk about the Earth's gravity.
Something has changed within me. Something is not the same. I'm through with playing by the rules of someone someone else's game. Too late for second guessing. Too late to go back to sleep. It's time to trust my instincts. Close my eyes and leave. It's time to try defying gravity. I think I'll try defying gravity, and you can't pull me down. I'm through accepting limits, 'cause someone says they're so. Some things I cannot change, but till I try, I'll never know. Too long I've been
The 17th century British scientist Isaac Newton made many contributions to the fields of mathematics, physics, and astronomy.
Look at that! They named another scientist. They're getting better at this.
Among the most important were his studies of gravity, the force of attraction that exists between all matter in the universe.
Here they are again, talking like they've seen all the matter in the universe.
What is gravity?
I have no idea. Okay, next question.
Wow.
No, here's the difference. We can describe gravity. We can say what it does to other things. We can measure it, predict with it. But when you start asking, like, what it is, I don't know.
Newton described the effects of gravity in his law of gravitation. This law states that the force of attraction between any two objects depends upon their masses and the distance between them. The larger the masses of the two objects and the closer together they are, the greater will be the force of gravity between them. The mass of the Earth exerts a force of gravity that pulls objects toward the center of the Earth. Weight is a measure of the strength of the pull of gravity on an object. Weight is measured in newtons. On the Earth's surface, a kilogram of mass weighs about 10 newtons. What is the weight of a 2 kilogram mass on the Earth's surface? The weight of a 10 kilogram mass? Weight and mass are not the same. Mass is the amount of matter in an object. Weight is the force of gravity on that matter. The mass of an object does not change with location, but its weight does. The weight of an object depends on its mass and its distance from the Earth's center. As the law of gravitation states, the force of gravity decreases as the distance from the Earth's center increases. For example, at 8,871 kilometers from the center of the Earth, or 2,500 kilometers above the surface of the Earth, a 1 kilogram mass weighs about 5 newtons, half of its weight on the Earth's surface. At 19,778 kilometers from the center of the Earth, or 13,400 kilometers above the surface of the Earth, a 1 kilogram mass weighs only about 1 newton. Weight also varies according to location on the Earth's surface. As you have read, the Earth spins on its axis, and the motion causes the Earth to bulge out slightly near the equator.
Oh yeah, I remember that.
Therefore, the distance between the Earth's surface and its center is greater at the equator than it is at the poles. This difference in distance means that your weight at the equator would be about 0.3% less than your weight at the North Pole. I must say, that's an interesting claim for sure. Let's come back to that in a moment.
Now, dark matter, dark energy. We don't know what dark matter is. It's 85% of the gravity of the universe is dark matter. Is something we don't know what it is. So we just call it dark matter. We don't know what. The universe has some pressure in the vacuum that's making it accelerate in its expansion against the wishes of gravity. We don't know what that is either. We call that dark energy. This sounds like we know something. We don't. I could call this Fred and Wilma, okay? It doesn't matter. We are dumb stupid about what these two things are. All right? Now, normally that's not a problem. until you look at this chart, okay? So everything we know about the universe, what we're made of, galaxies, stars, planets, that's all right here. So, according to this chart, we are 96% stupid in the universe. You're happy about that, apparently. I don't know what that means, you know. Are you applauding my honesty? Are you applauding, you're celebrating the stupidity of our species?
96% stupid about the universe. Okay, keep in mind, we can't say any kind of percent concerning the universe unless we know exactly what 100% of the universe is. While that was really interesting, what does that have to do with this claim about a variance in the Earth's gravity?
Well, it seems both the book and Neil Tyson forgot to mention how gravity is a fictitious force.
A fictitious force?
Yep, you heard me. Gravity is a fictitious force. A fictitious force is also called a pseudo-force or false force. It's also known as an inertial force. A fictitious force is a force that appears to act on a mass whose motion is described using a non-inertial frame of reference, such as an accelerating or rotating reference frame. An example is seen in a passenger vehicle that is accelerating in the forward direction. Passengers perceive they are being acted upon by a force in the rearward direction, pushing them back into their seats. Fictitious forces are like magic tricks.
Look who it is coming! The amazing Mumford! Oh, hey! Maybe he will do a trick for us. He does wonderful magic tricks, you know. Mumpy, it is your old pal Grover.
Yes, Grover.
Oh, it is so good to see you. Mumpy, maybe you could do something for us.
Well, I don't have much time, Grover.
This will not take long. I thought maybe you could do something for me and the boys and girls. Something like, maybe, hey, this carrot. Make this carrot disappear, would you please?
Oh, well, my. What a juicy, crunchy, delicious-looking carrot.
Mm-hmm.
Yes, indeed, I would be happy to make this carrot disappear.
Did you hear that, boys and girls? Oh, that is wonderful. And Mumpy, could you kind of make it do it with a big puff of smoke, kind of make it impressive?
Oh, all right. Stand back.
Yes, this is going to be so much fun. Okay.
A la peanut butter sandwiches.
Oh, look at all the smoke you did, Mumpy. That is wonderful. Did I not tell you?
There you are, all gone.
Oh, you have made the carrot disappear. Where is it? It is gone. He is so good. Okay, now make it appear again. Here we go. Bring it back. Bring it back.
I can't bring it back, Grover. I ate it.
You ate it? But Mumpy, that was not magic.
No, but it sure was delicious. And you didn't say anything about magic.
In a magic trick, an imaginary force, the magic, takes credit for something it didn't do. Centrifugal force is a good example of this. It's also known as a fictitious force. Here is a nice demonstration of that. If I were to be spinning around on a turntable and throw a ball, it looks as if a force causes that ball to move in a curved trajectory. This is an imaginary force, the magic in the magic trick. No force is actually causing the ball to move in a curved trajectory. This can be confirmed when we hop off the turntable and watch someone else throw the ball. From here, we can see the ball actually moving straight. The ball's path only appeared to curve before because you were spinning.
Oh, okay, that makes sense. Okay, so when you say gravity is a fictitious force, you're saying it isn't an actual force that causes things to fall. It is an illusion that is caused by something else?
Yes, that's what I'm saying. The notion of fictitious force comes up in Einstein's general theory of relativity. All fictitious forces are proportional to the mass of the object upon which they act, which is also true of gravity. This led Albert Einstein to wonder whether gravity was a fictitious force as well. He took note that if a person was free-falling in an elevator, they wouldn't be able to detect the force of gravity. However, if the elevator was rising, that's when he would feel the effects of gravity, and he would be glued to the floor. National Geographic has a great video clip that illustrates this beautifully. Here's a link in the top right corner if you want to watch that. Anyway, the free-falling reference frame is equivalent to an inertial reference frame, which gives us the equivalence principle. This is why Einstein referred to gravity as a fictitious force and said, acceleration and gravity are the same thing.
So that force you feel when you accelerate in a car, you can describe that as gravity?
Essentially, yes. A G-force, gravity force. In summarizing Einstein's suggestion with the rising elevator, he was saying we might not actually be falling, but rather the Earth could be accelerating upward toward us. In which case, on a globe, the Earth would be perpetually exploding or expanding rapidly in all directions. Unless it was us that was moving, in which case the Earth would be perpetually imploding.
That all seems so strange. Like, I just can't wrap my head around any of it.
Yeah, it is pretty weird. But that's Einstein for you. The main thing I want you to remember is that a fictitious force is an imaginary force that takes the credit of something else's work. Please keep in mind there are a lot of other things out there that can cause things to fall. For example, many people often don't realize everything is magnetic.
We often classify materials as either being magnetic or non-magnetic, but that's not entirely accurate. See, inside an atom, electrons are constantly buzzing around creating little loops of current. And because of the relationship between electricity and magnetism, that current produces a magnetic field for each electron. Under most circumstances, the direction of all those magnetic fields are random, so they just cancel each other out. But when an atom is placed inside another magnetic field, it adds an additional force to the electrons. This essentially changes their motion so that the atom gets a tiny net magnetic field that opposes the external one. This interaction is called diamagnetism, and because magnetic fields pointing in opposite directions repel each other, it produces a teeny tiny repulsive force. Every material experiences this, from a block of wood to an iron bar magnet. But diamagnetism is only one type of magnetism, and it's the weakest. So there's also paramagnetism, where atoms become weakly attracted to a magnet in an external magnetic field, and ferromagnetism, which is probably what you think about when someone says magnetic.
Everything is magnetic. Water, air, people, wood. So I'll show you these effects of diamagnetism. Everything repels a magnet. I'll show you that. What I have here is a syringe full of water, and I have my strong magnet. I'm not going to touch the magnet too. I'm just going to bring it close, and the water is going to repel the magnet and get pushed.
Kind of looks like you're touching it.
Not touching it.
Prove it. Oh, there you go.
Let's push it back. Not touching it. Not touching it. So water repels a magnet. Another thing that repels a magnet is wood. So here's an ordinary block of wood. I'm going to bring the magnet close to it but not touch it.
Let's change that angle.
Okay. See how it's not touching it, pushing it away. Really see.
It's stopping it.
Push it away.
So how is it doing this?
So diamagnetism is a quantum mechanical effect, which I won't get into, but essentially it's repelling the magnetic field.
A universe without electromagnetism would come apart at the seams.
If electromagnetism was turned off, matter would dissolve.
Everything would just fall apart.
I could probably, with my superhuman strength, hold myself together,
but the rest of you are doomed. Electromagnetism not only holds everything together, it makes things feel solid.
When you touch something, that's the electromagnetic force as well. We have electrons in our atoms and they repel each other, and when you try to touch something, those forces keep you from actually physically touching it.
The reason I don't fall through the floor is not that the floor is particularly solid. Most of the floor is empty space. It's the electric forces of the atoms in the floor against the electric forces of the atoms in my body that hold me up.
Well, I can definitely understand that explanation much better than what Einstein was suggesting.
All right, back to the book. Why would gravity seem different around the North Pole?
It could be because there's a stronger magnetic pole there.
I agree. Now, gravity isn't just stealing credit from magnetism. Let's take a look at vibration.
When you hear the word levitation, you probably picture the hoverboards from Back to the Future or magic tricks like this, but gravity-defying technology isn't just the stuff of science fiction. It's very real.
Acoustic levitation uses sound waves to counteract gravity.
Acoustic levitation is unique because, unlike magnetic levitation, for example, it can effectively suspend both liquids and solids. But there's a small catch.
The largest object we've levitated has just been a 3mm bead.
But even at that scale, there are some exciting applications, like analyzing chemical reactions in suspension, the creation of better drugs, and even improved robotic arms that can manipulate tiny, delicate objects.
And you can trap an object to counteract gravity by creating a space where there's no force.
That's Chris Benmore, a physicist with Argonne National Laboratory who uses this gravity-defying technology.
Sound is a mechanical wave. When you're in a concert and the music is very loud, you can feel your chest vibrating. Basically, we are taking advantage of this force, manipulating ultrasonic sound waves to make the particle levitate. Each of these elements is a tiny loudspeaker, and we control very finely what they are playing. If you are careful, you can make all the waves to reach the particle at the same time and make it levitate. It was well known, even since the 30s, that acoustic waves could create radiation forces. And even from 30 years ago, people have been using acoustic forces to levitate things. The real novelty of this work is that we only need one side, a device with only one side. Previously, you needed two devices, so the levitated particle had to be enclosed by the acoustic elements. Here, for instance, imagine that you wanted to levitate something inside your body. So with this, you could apply a one-sided device on your body, as you would do with an ultrasound scanner. It could be any particle that is inside your body, and you can manipulate it without the necessity to create any cut or intervention.
Gravity is just a big glory hog that gets all the credit for the work of other factors.
Kiss me goodbye, I'm defying gravity, and you can't pull me down. Unlimited, my future is unlimited, and I've just had a vision almost like a prophecy. I know it sounds truly crazy and true, the vision's hazy, but I swear someday I'll be flying so high, defying gravity. So if you care to find me, look to the western sky. As someone told me lately, everyone deserves a chance to fly, and if I'm flying solo, wizard that there is or was is ever gonna bring me down. Look at her, she's wicked. Get her! No more so wicked, so we got to bring her
Thank you for watching.